So just reteaching this problem once more. I'm just going to reread it and kind of emphasize some points again. The rubber band is being stretched to pull on the 1 kilogram block, but it doesn't really matter what the weight or what the mass of this block is, because what we're going to be relying on here is this idea that we were talking about last time with the, inversely proportional or proportional relationships. So the inversely proportional relationship for acceleration was the mass here, and the proportional relationship with acceleration was the force here, okay? So we got to think about what it is that we're dealing with acceleration. Is it force or is it mass as we read the problem? So we're pulling on with a constant force, and then the acceleration of the block is measured to be 3 meters per second squared. Okay, so we got that. Now, when the block with an unknown mass is pulled with the same rubber band using the same force, so the force stayed the same, the acceleration is now 5 meters per second. So what changed here? The force stayed the same, the mass changed, the acceleration changed. So we're dealing with which? The proportional relationship or the inversely proportional relationship? It's the inversely proportional relationship, that's right. So if I increase the mass, the acceleration should do what?
Decrease.
It would decrease. And if I decrease the mass, the acceleration should do what? It should increase. Well, what happened here? We started with an acceleration of 3 meters per second, and the acceleration became 5 meters per second. The acceleration increased. Therefore, the mass of the unknown block will be what? Less. Okay, so we know our answer needs to be lower than 1 kilogram. Okay? By how much is the question? Well, the ratio of the accelerations will tell us. Okay? That will give us a scale factor. We just need to set up a ratio that gives us a scale factor that's going to decrease the mass. So what is that ratio?
Could it be y equals a over x?
No, I don't want to even mess with that. Okay? It would. So let's set up a ratio, in other words, a proportion, that is going to give us a decrease in the mass. Okay? So I want to set up a proportion.
No, it would be 1 over 3.
If I put the mass here, then the other mass will go below, sure. So we can put 1 kilogram, 1.0 kilogram. This is the one that we knew. Oops, kg. Okay, so the mass that we knew was on the bottom, which means the acceleration for the mass that we knew will be on the bottom on the other side. Agreed?
Yeah.
Okay, so that would be what? No, we know the acceleration. Acceleration is going to go on the left side. The acceleration for the mass that we knew is on the bottom, which was what? 3 meters per second squared. Except, this is inversely proportional. So that means it needs to go on the top, because it's inversely proportional. If it was directly proportional, then it would go on the bottom. Okay? I have to put the 3.0 meters per second squared on the top, because then on the bottom will be the 5.0 meters per second squared, because this is an inversely proportional relationship. So I cannot set up a directly proportional relationship in this case. Directly proportional will put the 3.0 on the bottom. Okay? Notice that this ratio that we just created here, okay, gives us a ratio that is smaller than 1, which means we have now our scalar multiple that is going to decrease the mass result over here. Okay? That's the concept that we needed to think about yesterday when I was trying to rush at the end of the period that I didn't get across to us. Okay? So now how do we solve proportions? Well, we can cross multiply usually, but also, if you think about it, all we have here on the right-hand side is divide by on this variable. So we can multiply both sides by this division here of 1.0 kilograms. And that's why yesterday when I was saying it doesn't matter what the mass is, it could be 6 kilograms or 200 kilograms. It doesn't really matter. We just multiply this ratio here of 3/5 times whatever the mass is here, and we have our scalar multiple times the mass, and we get our result. As long as we're thinking about the inversely proportional relationship, we will get the result. We don't even need to set up a proportion. We did, but that's okay. We have m equals, I multiplied both sides by 1.0 kilograms. The meters per second here divided by meters per second is gone. So I just have 3/5 times 1.0 kilograms, and I get, what? 0.6 kilograms. We have a smaller mass, which will give us a larger acceleration, as the concept states. Now we're done. No. No, no, no. Oh. Okay. So now this last problem here in the section, 2 rubber bands are being stretched to the standard length, cause an object to accelerate at 2 meters per second. The standard length just means their normal unstretched length. So you've just taken up the slack. Suppose another object with twice the mass is pulled by 4 rubber bands stretched to the standard length. What is the acceleration of this second object? Think about it. So how do we figure this out is the question. We are pulling with a force. The force gives us this acceleration of 2 meters per second squared. We have twice the mass on the other object, but we doubled the number of rubber bands. That doubling of the number of rubber bands actually doubles the force. If you remember back to when we talked about the experiment with the rubber bands, if I double the number of rubber bands, it doubles the force. Okay, I add 1 rubber band, I added another force. If I added 2 rubber bands, I added 2 more forces. If I added 3 rubber bands, I added 3 more forces. Okay, so I doubled the number of rubber bands, I doubled whatever the force was. Okay, so the force and the acceleration are related in what way? They're directly proportional, which means if I doubled the force, what did I do to the acceleration? I doubled the acceleration. Okay? So now I have twice as much acceleration as I had before. But I also doubled the mass. If I double the mass, how does that affect the acceleration?
Gets halved.
It halves the acceleration because mass and acceleration are inversely proportional. So if I double the force, I double the acceleration, but then I double the mass, which means I have the acceleration. What is the net result?
0.
I did nothing, right? Therefore, the answer is B.
I figured I figured they were trying to pull a sneaky one on me.
It's wrong.
Saying it's the
That's
standard
wrong.
plane.
That's wrong. You double the force, so you double the acceleration, but then you double the mass, so then you have the acceleration. And that's how you do that problem. You have to use the concepts. Okay, so that is it for, what are we on? Section 4.